Lecture 2.15 Mass, Force, Work, and Kinetic Energy. So in the last lecture, we derived an expression for relativistic momentum. We found that to calculate the relativistic momentum, you take mass times velocity multiplied by the gamma factor, where the gamma factor is for the speed of the particle u. So our result that momentum is the gamma factor times mass times velocity can be kind of interpreted in two different ways. The first, which is the way that we're going to think about it, is that mass is a constant. It's the rest mass. And so when a particle goes to a higher velocity, the gamma factor is multiplied by the mass times velocity to show the relativistic increase in momentum. The second way of thinking about it is to include the gamma factor in the mass term. So if you wanted to redefine mass as equal to gamma times the rest mass, then this is a relativistic mass that does depend on the velocity. It turns out that both ways of thinking about mass are, all the mathematics works out exactly the same. It's just how you interpret it. Most folks now tend to like this first way of thinking about it, that mass is constant, and then when you define the momentum, you've got to multiply by a gamma. And the second way of thinking about it, you could just simply write that momentum is mass times velocity, which is the classical definition, but allowing for mass to change with velocity. So you'd say m is just equal to gamma times m naught. We find this to be more confusing, and again, most textbooks tend to prefer the first way, and so that's what we're going to stick to. So throughout this class, mass is always going to be the rest mass. Whether there's like a sub-zero, like a naught there or not, doesn't matter. Mass is always rest mass. So we'll use m naught and m interchangeably, and they're both going to refer to the mass of an object when it's at rest. Okay, so Newton's second law. It turns out that Newton's original formulation of his second law, which was that the force is the time derivative of the momentum, that does apply to special relativity, so this works. F equals ma doesn't work. So you can show in a homework that if you start with this definition, that you can show that force is equal to gamma cubed times mass times acceleration. So the way that you would approach that would be start with, again, F equals dp dt, plug in for the momentum, gamma m times the velocity, plug in for what the gamma factor is, and you get this expression that depends on velocity. When you carry out the derivatives, you can show this result. So it's fairly straightforward, just taking that derivative. Okay, work. This definition of work also applies to both classical physics and special relativity. So work is the integral of force through a distance. That works. The work kinetic energy also transfers over to relativity, so that's good. So, the change in the kinetic energy is going to be work done by the net force acting on the object. So we're going to use the work kinetic energy theorem to find an expression for the kinetic energy. So we're going to assume that we've got a particle that's starting at rest, so the initial kinetic energy will be 0. We'll apply a force, integrate it over its motion, and find the final kinetic energy. So kinetic energy is the integral of f dx. We're going to use our expression for Newton's second law, plug it in. So remember, the force is the time derivative of the momentum. So we're plugging in for momentum, gamma mu. We're going to move this dt over under the dx, leaving just a differential here. Dx dt is just the velocity u. So this dx dt comes over here to that u, and then again we have a d gamma mu. We can integrate this by parts to show that this first term right here, so we're equating u with u, and v is going to be gamma mu, just from the standard integration by parts formula. So when you apply integration by parts, you get this. So this first term is evaluated between the velocity from 0 up to some final velocity u, and then again we're integrating the second one from 0 to u. So we'll plug in for the gamma factor. So here and here. This first term, when you plug in u, you just get u. When you plug in u equals 0, this term up here goes to 0. So this term just gives you this, mu squared times the gamma factor. The second term, you do like a substitution, right? So if you let, say, a dummy variable w equals 1 minus u squared over c squared, then the derivative of that would be minus 2w over c squared. Anyway, you do a substitution, and it's pretty straightforward to get this result. Again, you evaluate that from 0 to u. When you plug in u, you get this expression. When you plug in 0 here, you get 1 minus 0, so the square root term is just 1. So you get an mc squared here for when you plug in the lower limit, so you get a negative sign out in front, because it's the lower limit. Okay, so now we put both of these on the common denominator here, so we multiply this expression by square root of 1 minus u squared over c squared. So the square roots just go away since we're multiplying the two exact same terms, and you get an mc squared minus mu squared. Let's see here. The mu squared cancels the negative mu squared, and you get an mc squared left over. Factor out the mc squared, and realize that this term here is just like 1 over 1 over square root of 1 minus u squared over c squared is just gamma. So we factor out the mc squared, and we find that the kinetic energy is mc squared times the quantity of gamma minus 1. So that's our expression, our relativistic expression for kinetic energy. I must say it doesn't look a whole lot like the classical version, which is 1/2 mv squared. But we'll come back to that in a minute. So here's this expression. Remember, gamma has the velocity dependence. If you plot this as a function of velocity, you get this curve. So the kinetic energy starts at 0, and then as you get closer and closer, as the velocity gets closer and closer to the speed of light here, the kinetic energy diverges to infinity. So let's plug in some other limits. So when velocity is 0, the gamma factor is 1. So 1 minus 1 is 0, and the kinetic energy is 0. So that makes sense. If the particle is at rest, it has 0 velocity, it has 0 kinetic energy. So that's intuitive. When the velocity is much less than the speed of light, you can show that this result does simplify down to 1/2 mv squared. So that's a homework problem. So you just use the Taylor series approximation to the gamma term to show that. As the velocity approaches the speed of light here, the gamma factor goes to infinity, and so therefore the kinetic energy goes to infinity. So the kinetic energy diverges as you get closer to the speed of light. So this right here is why the speed of light is an ultimate speed limit in the universe. Nothing can accelerate up to the speed of light because it would take an infinite amount of work to bring the object up to that velocity. Okay, so let's look at this expression for kinetic energy again. We're going to distribute the mc squared through there, so we'll get gamma mc squared minus mc squared. This first term is called the total energy in relativity. So we're going to define the total energy, E, as gamma mc squared. The second term we're going to define as the rest energy, just mc squared. So plugging in for the total energy and the rest energy, we see that the kinetic energy is just the total energy minus the rest energy of the particle, or the total energy is kinetic plus rest energy. So these are very useful expressions for what we're going to do in the rest of the class. So what's going on is that we imagine that every particle has some rest energy associated with it, given by this dashed line, which is equal to mc squared. And then if the object is moving relative to your reference frame, then it will gain kinetic energy up and beyond its rest energy. So E equals mc squared is probably the most famous equation in all of physics. It says that matter and energy are equivalent in some way. So you can think that particles, massive particles, store energy in them, or maybe that massive particles are energy, depending on how you want to think about it. But that we'll see a little bit later on, you can actually create particles out of energy, or you can slam particles with antiparticles and they'll destroy each other and their mass will be converted back into energy. Okay, in atomic and nuclear and particle physics, when we're dealing with subatomic particles or atoms, most of the time energy is expressed in units of electron volts. So remember, an electron volt is the energy it takes for an electron to move through a potential of 1 volt. So the electron volt is equal to 1.602 times 10 to the negative 19th joules. You might recognize that as the fundamental charge there. When dealing with larger energies than this tiny amount, we can also use kilo electron volts, mega electron volts, giga electron volts, and tera electron volts. So these are usually pronounced KeV, MeV, GeV, and TeV. And so those range between 1,000 electron volts to 1 trillion electron volts. We can, now that we have our equation equals mc squared, we can express mass in these energy units as well. So if we solve for mass, it's equal to E naught over c squared. That's in joules per c squared. If you think about what the mass equivalent of 1 electron volt is, you can calculate it by dividing electron volt by the speed of light squared. So you get that electron volt per c squared is the equivalent of 1.78 times 10 to the negative 36 kilograms, a very tiny mass indeed. Just like in energy units, it's more common to work in keV per c squared, MeV per c squared, and so on. So let's actually calculate the rest energy of the electron. So again, the mass of the electron is 9.11 times 10 to the negative 31 kilograms. We can multiply that mass by this conversion factor that we just calculated on the previous slide. When you do that, you get 5.11 times 10 to the 5th electron volts per c squared. So let's convert that into MeVs. So that's 0.511 MeV per c squared. And this is a very common way of expressing the mass, like in atomic and particle physics. You can do the same thing with a proton, 1.67 times 10 to the negative 27th kilograms, multiply it by the conversion factor, and you find that it turns out to be 938 MeV per c squared, so almost a giga electron volt. So here's a table showing some other particles. There's the proton, there's the electron, proton and neutron. The alpha particle is a helium nucleus. And muon is a cousin to the electron, quite a bit heavier. And the deuteron is like the nucleus of deuterium, so a proton and a neutron in the nucleus. So we're going to come back and look at some of these numbers in a little bit more detail later in the class. So here's an example of how to put some of the stuff into practice. Suppose you wanted to find the total and kinetic energy of an electron that's moving at 99% the speed of light. It's pretty simple. So we know its velocity, so you can immediately calculate the gamma factor, plug in 0.99 for U over C, so you get a gamma factor of 7.09. Total energy is simply gamma mc squared. We know that the rest energy of the electron is mc squared is 0.511 MeV, so we know mc squared here for the electron. So now all you have to do is multiply the gamma factor by its rest energy to find that the total energy of the electron is 3.62 MeVs. So quite a bit larger than its rest energy, which is only 0.511 MeVs. The kinetic energy is the difference between the total energy and the rest energy. So we can just subtract 0.511 from 3.62 to find out that the kinetic energy of our electron is 3.11 MeVs. So most of the energy of this fastly moving electron is in kinetic energy, not as much as in its rest energy. Here's another example. The Stanford Linear Accelerator, SLAC, had an accelerator to accelerate electrons down this linear geometry. It's no longer they've actually converted it into an X-ray laser now, but when it was accelerating electrons, it could get them up to 9 GeVs. So the question is, we want to find the velocity of an electron if it has a total energy of 9 GeVs. So you can start with this equation for the total energy. We're trying to solve for the velocity, which is buried in the gamma factor there. So to solve for gamma, we're going to divide both sides by mc squared. So gamma is the total energy over E naught. We're going to use beta instead of V over U just to make it a little bit simpler. So we've got 1 over the square root of 1 minus beta squared is E over E naught. So we know the energy of the electrons and we know the rest energy of the electrons. We're still going to keep it in this form though and plug in the values at the end. We want to solve for beta. So just cross multiply, square both sides, subtract from 1. You get this. So now you can plug in for E naught over E. So E naught is 0.511 MeVs. And E was 9 giga electron volts, which is the same as 9,000 mega electron volts. So when you do this calculation, you get that the beta factor is not 0.999999984. I think I got all the 9s right there. So it's going at nearly the speed of light, just slightly under. All right, so that's it for this lecture.